if you think about this being a piston, and we've got an arm here, or arm that's three of this particular item. So what we did yesterday, and this chapter is going to take me a little longer as I have been working through the material. I think we're fine as far as due dates on the homework, but we are definitely going to be working on this material a little while longer, because it gets a little messy and it gets a little complicated. The work doesn't get messy and complicated. It's just picturing and figuring out the problem that we're dealing with that gets a little messy and complicated. And we're going to use this one to help us out for a while. So what we have is got an engine, we got a crank A and B, has a constant clockwise angular motion of 2,000 RPM. And what we're going to do is we're going to determine the angular velocity for the segment BD. Okay, the segment BD, and we're gonna play with it, and then we'll come back to this problem over and over and over again as we start working through a variety of different aspects. So I'm going to give you a second to kind of draw the general sketch, and we're going to end up breaking it apart and doing different pieces of it. I'm giving you just a bit of time to get that sketch done, because I'm not planning on writing on my sketch so that we can come back to it several times. All right. So I'm going to draw this in pieces. So if you remember when we dealt with frames and we dealt with machines, we could break things apart. So we're going to break things apart. So I'm going to have our component like this. So this is A to B. This is 3 inches. We're told that this is 40 degrees. And we're going to have a velocity at B. Okay, we've got a velocity at B. One of the things is we've got the angular, we're told that the angular velocity around AB was 2,000 revolutions per minute. And we're going to go ahead and get that into our normal units. So that's radians per revolution. And then we got 1 minute is 60 seconds. So I'm going to end up at being 209 radians per second. Now, if I'm looking at this piece, I can go back and say that my velocity is just going to be my radius, omega AB, and this is going to be 3, and I get my 209.4 radians, and this is now inches per second. And this gets me 628.3 inches per second. So I've just looked at this component right here, but let's look at that component a little bit more. So this is A, this is B. There's my velocity, VB. That's a right angle. This is 40 degrees. So if I give myself a reference point, this is going to be 40 degrees. 40 plus 90 is 130, so this ends up being 50 degrees. So we're going to play with this a little bit. Because next I'm going to look at B to D. I've got a velocity of the piston, VD, because it's fixed going this direction, okay? It's fixed going this direction. And one of the things that I now know is I've got my velocity VB, and we know this angle is 50 degrees. And we currently don't know this angle, and we're calling that a script beta. Okay? So this is my segment that's moving around. So I'm going to draw this again. And what we're going to do is we're going to break it out into translational and rotational motion. Okay? So we're going to break it out into its two components. My translational motion, I've got my VB. That's going to say that I'm taking this and I'm just moving it along the same line as before. So I've got my VB here, I've got my VB here. Okay? That's going to be my translational motion, and we know that this is 50 degrees. And we know that this is 50 degrees. So that part of the problem is okay. It's when we get to the other part to deal with the rotational motion that things get a little wonky. So I've got my length L. I now have my velocity VD is going to come into play, but that's going to cause me to have motion that looks like this, which is going to give me a resulting vector VDB. I'm going to get my angular BD as I'm rotating, and that's the length of my rotational motion. So this is the general motion. And now we've broken it up into rotational and translational motion. But we're gonna have to take care of some things and use some geometry to help us out. And one of them is this right here. Okay, that part of our diagram right there. So let's take that diagram and let's expand it out. So I've got VD inches. We have VB. We know that this is 50 degrees. Okay. We know that's 50 degrees. If I put in the other part of my diagram that I had before, okay, so now what we've got is we've got a triangle. Okay, we've got a triangle in our system. We know that this is 40 degrees. Right? Okay, we know that's 40 degrees. This is my beta. And this side is got my 3 inches in here for that, for this side of it here, right there. It's got my 3 inches, so this is not drawn to scale. Okay. So I can get a triangle that looks like this. So that's 8 3, we got 40. I can use the law of sines. Sine of 40 degrees over 8 is going to equal the sine of beta over 3. So I get 3 sine is going to give me the sine of beta, which is going to give me beta is equal to 13. So I'm going to redraw my picture here. So I have my vector VD, my vector VB. I'm going to take my vector VB, okay, so I'm just going to do a vector triangle here, all right? I'm going to do my vector VD. So this is VB, this is VD, which means that I'm going to have my vector that I'm looking for, vector DB. So I have a forced triangle that kind of looks like this. From the horizontal to here, we've already figured out that that's 50 degrees. Which means that this is 50 degrees. Right? If I make that a right angle, right there, that makes that 40 degrees. And from this right here, we found the beta, and it turns out that this, and you can play with it and prove it to yourself, that is my 13.95 degrees. So I've got 50 degrees, I've got 40 degrees, 13.95 degrees, which means that this whole angle is going to be the 40 degrees plus the beta, which is going to give me 53.95 degrees. And this is just a vector. This is one of those vector triangles that we've used before to solve the problem. And it's going to come up and help us out, because now I can use the law of sines. I get the sine of 50 degrees, vector DB, is equal to the sine of 53.95 degrees, VD, which is equal to the sine of 76.05 degrees, which is VB. And that comes from this. That's 180 minus 50 minus 53.95 is going to give me my 76.05. But I've already figured out, and I'm given, or I figured out vector VB. That's right here. So now I can just plug it in and get vector VD is equal to 523.4 inches per second. And vector DB is going to give me 495.9 inches per second. And then VDB is just R omega BD. So I'm going to take my VDB divided by R. It's going to give me my omega BD. And this gives me 62 radians per second. So what we did was we looked at the translational plus the rotational motion to help us solve the problem. And that's where we're looking at and where we're approaching other problems, because what we're going to end up doing is solving problems that look kind of like this. Things that we've done since we're in grade school. I've got a box. We're going to move the box along the way. Key is without slipping, okay? We're not going to have any slip. So as I pull this box, we know that these rollers are going to rotate.
I don't remember doing this in grade school.
Yeah,
Now, didn't you take a block? I mean, you took the little yellow, everybody had the different shaped blocks. You took the red block, right, or the blue block, and you put it on the little orange, if you did it in the color-coded ones. The little orange blocks, you could put the little rollers on there and take your block and roll it along the way, right? This is the way they said how they got the big stones moved for the pyramids, right? We used a roller and we put the block and we rolled the block along the roller.
I think the only time I ever played with logs as a kid was with Lincoln logs.
Oh my God, this has notches in it, but just a regular blocks, you know, if there's a round block, you know, there you go. Okay, so we got blocks with a roller. And what we want to do is we're given this in terms of its velocity, and what we're wanting to do is we're wanting to figure out what's happening on this roller as we move this. So we want to figure out the angular frequency in terms of the linear velocity. Okay, that's what we're after. But we're going to have to look at the motion of our roller and kind of know what the motion of our block is. Our block's just going to go this way, right? Got to look at the motion of the roller. So we're going to look at the roller by itself. So let's look at the roller by itself. And basically what's happening with our roller is we're going to rotate the roller. It's going in the other direction, but we're going to rotate the roller and we're going to move from this point to this point. But the distance that gets translated is going to be SG. That's our theta. So let's kind of walk through that a little bit. So even though our situation is going the other direction, let's just look at that cylinder and kind of follow what's happening. So if I have this cylinder that's rolling this way, and it started here, as it rolled, okay, if I take my pin as it rolled without slipping, I'm going to get translational motion and I'm going to get that rotational motion. Okay, I've taken my pin, I'm just rolling it without slipping, and if I look at the center, I'm going to have it move. So this is our first position. This is our second position. And if I'm looking at it from point A, this is the distance that I've moved, which is my SG. Okay? And this is now parallel to B, or perpendicular to B. The rotation is related to my lovely angle, and so I can do my SG is equal to R theta. Okay, and for rolling without slipping, I can get VG, which is just going to be DSG with respect to time, which is going to give me RD. Right, which is just going to give me R omega. And I can similarly do AG, which is going to give me R alpha. So we can use what we learned here to help us with our roller. So I have my roller. this is the velocity of the box. Okay, that's the velocity of the box. This is the center of my roller. This is a distance r, and that's a distance r. As we roll, this is going to move to a new location. And we can kind of draw a triangle that looks like this, and that's the angle through which we rotate. So if I look at the R of the roller, this would be my SR, and this is going to be related to the distance of the box. Okay. My roller is just going to be R theta. My box is going to be, because I'm 2R away, so it's 2R theta, or it's going to be twice the roller. So now if I do ds box, which is going to give me the velocity of the box, that's just going to be d2r theta with respect to time, which is going to be 2r d theta with respect to time, which is equal to 2r omega. So 2 times the radius divided by the velocity. So I'm going to try and keep my notes. Examples with that gave us the motion, and it broke it out into translational and rotational. This is called absolute motion. Okay? It's absolute motion, and the analysis is formed on the whole system. And we broke it out into the individual parts. The other thing that helped us out was we were dealing with outslipping, which is going to help us out, okay? But we can actually now look at it with 2 sets of axes. And this is going to let us work, but because basically what we've done is we've did the analysis looking at everything in the same configuration, but now we can deal with 2 sets of axes, and we can start dealing with relative motion and have relative motion help us out. Okay, we can have relative motion to help us out a little bit. So we're going to take a wheel. Okay, so we're going to take the wheel, and we're going to give ourselves and look at how B is happening, how our translational motion is going with respect to that center part, and we're looking at how we're rotating the system. So it's very similar, but what we can do now is that the velocity of B is going to equal the velocity of my center of gravity. There's my translational motion plus my rotational motion, where I'm using a relative definition of the position that I have from A to B. And if I have my wheel here, we have a fixed radius. Radius is 0.6 meters. We're rotating around with an omega. We're going from, and I can write that out in vector notation, and it's going to be minus 0.6 I, Because if I'm writing this vector, this relative vector from A to B, that's it. And we're given that omega, by the way, is 10 radians per second. But if I want that in vector form, remember I'm going to use my right-hand rule, and in this case, because I'm going in the wrong direction, this would actually be written as minus 10 in the k direction. So everybody with me where I get my directions all in place.
Why would you put it as K?
Right-hand rule, rotational motion. Remember, my rotational motion is going to have right-hand rule. I'm going into the board. If I'm calling this X and Y, I'm going into the board and it's K,
Gotcha.
which is why it's negative. So now, set up to be able to do my and this is going to give me, when I do this, I end up with a positive 6i and a positive 6j. Now in this case, how we've set the problem up, in this case, we are rolling without slipping. And I'm going to end up with my VG is equal to 0. And I'm going to end up with B is going to just end up being my VG plus my omega plus RBA, which is now my 6I plus 6J, which is going to get in the magnitude of VB is then going to be the square root of 36 plus 36, which is going to give me 8.49. meters per second. Now this is the vector analysis way to do it. There's another way to do it, which is a scalar analysis way. Okay? Scalar analysis way. And if I do it with my scalar analysis, I end up looking at a triangle that looks like this. I get R, this is 45-degree angle. And I will get VBX is going to equal 10.6 divided by the cosine of 45, and that's going to be times the cosine of 45. And you can kind of play with that to kind of get to the same place. And you get VY the same way. Okay, so this is the one we're going to tackle. I've got a gear, and we want to find the velocity of VO at the instant shown. So we're moving this 4 feet per second. We're moving it this way 3 feet per second. We want to find the motion of this at the moment shown. So if I draw my picture, this is one of those cases where learning how to draw the picture is really going to help. So this is my VO. This is my V at B. So we're going to call this point B. We're calling this point C. And we got V of C. V of C is 4 feet per second. V of B is 3 feet per second. And we're wanting to find V of O. Well, V of B is going to equal what's happening at V of C plus the rotation that I'm going to be getting associated with that, and that's R O of C. Because I'm going to be rotating around this point. Okay, so there's my rotation. I'm going to be rotating around that point. We don't know omega, all right, but we do know my R. Oh no, this is RBC, sorry. That's RBC. So I'm going to write RBC first. Okay, RBC is pretty easy. That this radius to here is 0.75 feet. So RBC is going to be my 1.5 plus my 0.75, and that's in the J direction. And that's going to give me 2.25 J. VC is equal to minus 4 in the I direction. VB is equal to 3 in the plus I direction. And omega is omega in the K direction.
How do we know that the velocity is in the J direction?
No, that's an I. It's not an I.
Oh, sorry, R. Sorry.
R?
The R is in the
If I'm making this the I direction, that's got to be in the J direction. If I'm doing my relative vector from here to there,
Oh, okay, yeah.
Why is it 1.5 plus 0.75?
okay, because if you're looking at because we're given, if I'm doing it from here to here, and I'm going from there to there, so 1.5 gets me to the center. From the center up to where B is, it's another 0.75. Okay, now because this is moving faster, right? We're pretty sure it's going to rotate that way, right? Which means that that's going to be a negative. Because our convention is the other way around. So now when I do omega cross RBA, I have that. This is going to give me 2.25 omega in the I direction. So now, oops, that should be a cross, not a plus. Make my notes pretty for the screen. So now VB is minus 3 in the I direction. And I have, or no, it's plus 3 in the I direction, minus 4 in the I direction, plus I direction. Since everything's in the I direction, I get 3 is equal to minus 4 plus 2 for omega, and omega equals 3.11 radians per second. And because it's positive, that tells us that we picked our direction correct on the diagram. If it had been negative, that said I picked my direction backwards.
So your answer will always be positive.
No. If it turned out negative, it said I picked my direction bad.
But what I'm saying is like the correct answer is, it's like if you typed it on WebAssign and you typed in negative 3.11, it would say check your signs.
It might.
Um,
But it'll be the same numerical value like the magnitude.
Yeah, the magnitude will be the same.
But if
It's,
you-
it automatically assumes that counterclockwise is positive.
Right.
usually. It'll state which one is positive.
Yeah, and it'll probably say, is this, which way,
but
If
you
it
always,
may-
you always want your answer to be positive. That's what I'm saying.
I don't know.
It's like if you get a negative time. Okay.
Yeah, negative time is not real.
Yeah.
All the negative, all
It's rotating counterclockwise instead of
clockwise. Yeah, that's what the negative would tell me here.
So if on the question online it says, tell if your answer is going clockwise or counterclockwise with a positive or negative sign, it tells you like which one should be positive, which one
Yeah.
negative based on direction, then you just have to know the correct direction with the correct sign.
Okay.
And a lot of times it says, tell me if it's this, and then is it counterclockwise or clockwise. I mean, it actually asks you. In this case, it's clockwise. And then, if we want to know VO is going to equal VC plus omega cross ROC. And then we can actually, this ends up being -4, and this is plus. Now we know this is a minus 3.11 K crossed 1.5 J. You just work out the problem and you'll end up getting that 0.667 in the I direction. And that's in the I direction. Okay. So we're going to work through this one. And ultimately what we want to find out is the velocity at D. And we're going to figure out some angular accelerations along the way. We're going to find the velocity at C and the rotation of AC. And we're going to find the rotation around CD. So this one's actually problem 79. Give you just a second. Okay. So the first thing I'm going to do is we are given some information. We're given that VA is 20 meters per second. We don't know what VC is, and we don't know what VD is, but we can actually do some things to get there. So I'm going to write out VC. So I'm going to write out VC. VC, because I'm going to have it going this way on my diagram. So basically what I've got is VD, and this is VC, And this is, we're given that this is 30 degrees. Okay, so essentially what I'm doing is I'm extending this out. I'm making my VC go this direction, so I'm going to get a 30-degree angle up here. We know that this is a 45-degree angle. And we're ultimately going to have to figure out omega CD. So VC, I'm going to give myself a little bit of room, is going to be negative VC cosine of 30 degrees in the I direction plus VC sine 30 degrees in the J direction. VD is easy enough because it's only in the J direction. So I've got that part. I'm going to go ahead and write out VA. Okay, VA. We've got this piece here. And this is a little hard to tell, but this is the angle I got to use because this is directly in line with this piston right here. Okay, so my VA is minus 20 cosine of 45 degrees in the I direction plus 20 sine 45. And then I've got to have RAC. And if I'm drawing my picture for this, here's my VC. This is my VA. This is 30 degrees. I'm going to have the rotation go around here, so that's my omega AC. And the length of this sucker is 300 millimeters. So when I do RAC, that's going to be minus 0.3, because I'm going to convert it to meters, cosine 30 degrees, plus 0.3 sine 30 degrees in the J direction. So now I've written out all my vectors. And we know that VC is going to equal VA plus my omega AC cross with my RAC. So I'm going to do this part first. And this becomes minus 0.2598. This is 0.150. That is just doing the calculations for that right there. That's a 0. This ends up giving you a positive 0.15 omega I minus a 0.2598 omega J. If I do the numbers here for VA, so VC is going to equal 1.41 I plus 1 point, or that's a minus right there, minus 14.14 J plus 0.15 omega I minus 0.2598 omega J. Adding my I's and my J's together, I'm going to get a negative 14.41 I plus 0.015 omega in the I direction is going to equal minus VC cosine 30 degrees in the I direction. Putting all my I's together. I'm going to get my 14.14 plus my negative 0.2598 omega is going to give me a positive VC sine 30 degrees. All these are in the, this is the I direction, this is the J direction. I now have two equations, and I can solve for my omega and my VC. And when I do that, VC equals 19.32 and omega AC equals 17.25. Now I can do the VD because VD is going to equal VC plus omega CD cross RCD. So I got to figure out RCD. That's going to be minus 0.15 cosine 45 degrees in the I direction, 45 degrees in the J direction. And that ends up being minus 0.106. We do the same analysis. And when I get that, I end up with 0.106 omega I plus, it's actually minus, and you'll end up two equations, two unknowns again, and you get 157.74 radians per second for omega, and you get 7.07 meters per second for VD. Now again, we've been doing kind of the, we've gone from absolute motion to relative motion, and we can simplify life a little bit more if we can find something that helps us exclude things. So if I start with my equation that we've been using, that we've been working with for velocity, VB is equal to VA plus whatever rotational motion I've got. If I can pick a point where that's equal to 0, life can become a lot easier. So if I can pick a point where this A is 0, I can simplify things a lot. And if we do this, this is called, the point that we want to look for is called the instantaneous center of zero velocity. Okay? And we can also, that point that we're looking at, that point is going to lie on the axis of zero velocity. So I'm going to show you the figure that the book gives us. And what's really cool about it is you can actually physically see it. So we got a bicycle wheel, and as the bicycle is translating down the way, there is a point where the individual points, i.e. you can see the spokes, and the spokes don't appear to be moving, whereas up here the spokes are blurred. This is going to give me my point of zero velocity. So if I'm working problems to figure out how other things are working, to be able to say, okay, if I'm working from this point, I can help our fact a great deal by being able to get that spot. The trick comes to figuring out where that sucker is. All right? The real trick comes to figuring out where that piece is. And if you guys go to page 362, so you're going to go to page 362 or 361, sorry, 361 in your text, it's going to talk about where the location of this point is going to be. And it starts by looking at, all right, if I'm traveling along this line, I can find, looking at this point, I'm going to have a nice perpendicular. I know this angular rotation and that velocity. If I know the velocity at A and I know its rotation, I can find this point where the velocity is equal to 0. I can do it again if I'm finding the location of the point where if I know VA and VB, I can come back and find this point, VIC. And then you can deal with it if I'm going around a circle here, rotating around this axis, I can also find my point. And then you can do some really creative mechanics to find the point as well. So I encourage you to go look at page 361 because it talks through it a little bit. But we kind of want to go back and look at it and figure out how to get these things. But if once I've got it, it simplifies my problem a lot. And so what we're going to do, given that our time today, I'm going to do 2 problems. And then we'll come back and continue to work with this because this is the part that, as I was working through it, I'm going, okay, it's one of those to get your head around. You got to work a few problems. Because otherwise it takes a little bit to kind of go, okay, how am I really going to use this? How am I going to play with this? And how am I going to find it? And so we're going to do that, and then we'll come back tomorrow and we'll do it again. And I'll give you a different way to look at this instantaneous velocity. Before, right? We've got a gear here. Let me look. Not quite the, yeah, it's just a hair different. No, it's the same. So we're back with our gear here. We're going to use this gear again. Except we're going to use a little bit, some different numbers, but it's kind of that same configuration. So we've got our gear. Kind of looking at it from that perspective. It's very similar. My measurements are going to be a little different, but that's all right. Oh, let's do a better picture. Much better picture. I've got a velocity VB. We've got a point C. I've got a point velocity. This is VA, and we're actually given that VA is going to be 1.2 meters per second. This distance from here to here is 250 millimeters. This distance from here to here is 150 millimeters. this angle is 45 degrees. This is going to be RCD. And since the gear is rotating on a stationary surface, we're told that VC is equal to 0. Okay, my gear, VC is not going to go anywhere. I'm going to get rotating around, but VC is not going to go anywhere. So the point C is a point of no velocity, just like in our bicycle wheel. And when that happens, VA simplifies really, really nice. And VA is just going to be the radius divided by that. I can find this around there, and that's going to be my 1.2 meters per second divided by my 0.15. It's going to give me 8 radians per second. Now that I've got my V of A, or my omega of A, right, my 8 radians per second, V of B becomes really easy. That's RVB omega. V of D becomes really easy. That's RV or RD omega. RB in this case is my 0.25 meters. 8. It's going to give me 2 meters per second. This right here is going to be my radius, 0.15 times the square root of 2 times 8 is going to give me 1.697 meters per second. So it simplified things dramatically by being able to note that VC was 0.
Why is BC 0?
Because it's not going anywhere. If I'm moving this gear, this point's staying put, just like on the bicycle.
It'll eventually go somewhere, but for right now.
Well, this is actually a gear. It won't. If I have this locked in place, that gear, that C is not going anywhere. If it's on a shaft, this is a shaft and it's a fixed shaft. I pull this, that point's never going anywhere. Think about it. If I'm cranking something, if I'm sharpening a pencil, right? There's always a point C in contact with
Oh, so it.
that point. Never goes anywhere. The teeth will move around.
Yeah.
The teeth will move around, but that point's right there the whole time.
It's kind of like the thing is always moving, but it's always staying the same because that point is always constant.
That point's constant. The teeth aren't. You know, whether tooth 1 or tooth 20 is there is going to be different. But point C will always be right there.
It's called a racket thingy, by the way.
Oh, that one, yeah. Just a gear.
And what is that 8 value?
The 8 value, it's my omega. It's my angular velocity of the gear. I think I'm going to save the next one for tomorrow.